So we were talking about reaction coordinate diagrams last time, right? And we ended on like exergonic or endergonic reactions. We can also get kinetics data out of our reaction coordinate diagrams. Now, usually when I say kinetics, everyone kind of shudders because they remember Gen Chem and like ice tables and stuff. Yeah, we're not doing that. I didn't share the screen. Yeah, you are. You are. This is now two classes in a row. I forgot to share my screen. It's awesome. I'm getting like worse at this as I go. This is great. It's great. Better. Okay, so if you remember, kinetics is the study of reaction rates. So we can use reaction coordinate diagrams to determine the relative rates of different steps in a mechanism, right? And we do this by looking at something called activation energy. Activation energy is kind of abbreviated E sub A, right? This is the energy barrier needed for a reaction to proceed. Right. So we have to get over this energy barrier, this activation energy, for the reaction to go forward. So what we can say is that high activation energies equal slow reactions or slow steps, and low E sub A equals a fast reaction slash step. So we can look at a reaction coordinate diagram, say, hey, this activation energy is higher than this one. So the step with the highest activation energy is the slow step. So the slow step in a mechanism is the rate determining step. Your reaction can be no faster than its slowest step. So you find the step that is the slowest, and that is kind of the limit for how fast your reaction can go. That's going to determine the rate of your reaction. So if we look at a reaction coordinate diagram, how many steps do we have? 2 steps, right? I've got 2 transition states, right? So 2 transition states equals 2 steps. Your activation energy is measured from your starting material or intermediate the energy of that to the top, to the transition state. So for this first step, our activation energy is from the starting material to that transition state. Second step, same thing. So this step is the slow step because the activation energy is higher than the second step, right? So you can think of it as you need a lot of energy to get your starting material over the first transition state. But then once you get to the intermediate, once you get to the intermediate here, right, there's a bunch of energy. Those molecules had enough energy to get over that first really big barrier. This small activation barrier isn't really going to stop them at all. So as soon as you get over that slow step, you do that first slow step, that next step is going to be super fast. It's going to happen almost instantaneously. So it's like there's really not a barrier to that second step at all because it's so much smaller than the first step. All right. So you usually think about your fast steps in your reaction happening nearly instantaneously compared to the slow step. So you basically don't worry about how long it takes to do your fast step because you only care about your slow step. All right. How many steps does this reaction have? 3 steps. All right, I've got 3 transition states. 1, 2, 3. 3 transition states equals 3 steps. All right, I've got 2 intermediates here and here. Right, and I have an activation energy here, an activation energy here, and an activation energy there. Which step is the rate determining step? Which one is the slowest step? 2. So this is our rate determining step. Right. We can also, it's pretty clear, right? You could say that the third step is the fastest of the 3 steps, right? It has the lowest activation energy. Then the first step, and then the second step is the slowest, right? Because it's pretty clear that those activation energies are different. We don't ever, we're never going to get any numbers out of this. This is all kind of just like qualitative, like just looking at it and saying, hey, which one's fast, which one's slow, but we're not going to get a actual rate number out of it. So in the early class, someone asked me how would you be tested on reaction coordinate diagrams? And I did 2 different types of questions for these. One is I will kind of describe the reaction coordinate diagram to you and say, hey, this is a reaction that has 3 steps. The reaction is, if it was this one, is this endergonic or exergonic? Endergonic, right? I'm going to put energy in. I'm uphill. My product's a little bit less stable, so it's endergonic. Right, so I'd say how many steps there were. I would say if the reaction was endergonic or exergonic. I would say, hey, there are 3 steps, and the second step is the slow step. And the third step is faster than the first step, right? So then you would have to draw all your heights accordingly, right? Or the other version of this is I give you a reaction coordinate diagram, and then I just ask you questions about it. I'm like, label all your transition states, label the intermediates. Is it exergonic or endergonic based on what you see? Which step's the fast step? So those kind of things. So I can either have you build one from a description, or I can have you describe one from the actual drawing. We'll see exactly what I end up doing when I have to make this in Moodle. We'll see how that goes. But it's going to be some variation of one of those two things. I don't like to see myself coming up with some crazy third thing. Okay. So we can do rates. We can also talk about stabilities from reaction coordinate diagrams. And there are two types of stability. There's thermodynamic stability, right? And this is just looking at which compound's lower energy. So the general rule of thumb when you think about thermodynamic stability is high energy equals less stable, low energy equals more stable. So this is just looking at your height on the y-axis on your reaction coordinate diagram. So if you have, right, you could say, hey, my starting material versus my product, my starting material is lower on the y-axis than my product. So I can say my starting material is more stable, right? So this is just how far up are you on the y-axis? Are you more stable or are you less stable? That's thermodynamic stability. Right? The other type of stability is a little bit harder to think about, and that's kinetic stability. And this is how likely a compound is to react. Right? This, you're looking at the activation energy for the next step of that compound. So high activation energy equals high kinetic stability. Low activation energy equals low kinetic stability. Right? So when you have a high activation energy, it's going to take a lot of energy, a lot of oomph to make that compound react, right? Because it's got a big barrier. It's just happy staying where it is. A low activation energy, right, means that compound, it's easier for that compound to react. The barrier that's keeping it where it is isn't very big, so it's easy to get over it and go on to a new compound or to do something, right? So imagine, if you will, that you have a roommate who's a pothead or a roommate who's a meth head. Your pothead roommate has high kinetic stability, right? You know, if you go home on the weekend and you leave at Friday at 5 p.m., your roommate is blazed on the couch, just like, yeah, man, I'm one with the couch and the universe. All is cool. And you know, they're not moving. Like the house is going to have to burn down to get them to move. They are comfy. They are good. They are not going anywhere. They are kinetically stable. You know where they're going to be. On the living room, watching Netflix, eating Cheetos. They're there. You have a meth head roommate. You don't know where they are. They're just like, yeah, man, let's go. You see them. They're here. They're there. Your PlayStation's gone and sold. You don't know what's going on. they have low kinetic stability. They're just going, right? Pothead roommate, better roommate. They'll just eat your snacks. They won't sell your stuff. Oh, this is, don't do drugs. Don't do drugs. Okay, I'm safe now. But yeah, so pothead roommate takes a lot of energy to get them to move. Meth head roommate doesn't take much to get them to go crazy. Molecules the same way. High kinetic stability takes a lot of energy to get them to move. Low kinetic stability, they will just go react and go do something. Someone made fun of my pothead thing, and I was like, hey man, I've never done drugs before. I don't know what that's like. I just have TV. All right. We feel pretty good about reaction coordinate diagrams.
I got asked to clarify thermodynamic and kinetic stability one more time.
Thermodynamic stability is just kind of the absolute, like, how far you are up on the y-axis, right? So if this is energy, right? This is more stable than this, whatever this compound is, because it's lower in energy on the y-axis. So yeah, it doesn't impact rate. It's just kind of an absolute what is lower in energy. Where kinetic doesn't matter if, like, you can be lower in energy but have a low kinetic stability compared to, like, the higher energy thing. The higher energy thing could be more kinetically stable. It could be harder to do the next step of a reaction, but it could be less stable to begin with, if that makes any sense. So now we're going to go back to our alkene reactions. We're going to start working through those. So we're going to start with that same reaction that we used to kind of model the mechanism for the reaction coordinate diagrams. So we're going to start with hydrohalogenation, right? You add H to one carbon of a double bond and X, a halide, to the other. Right, so you're adding HX across your double bond. Hydrohalogenation. Hydro, you're adding a hydrogen. Halogen, you're adding a halogen. Right, so our example, kind of our go-to, is taking butene, reacting it with HX. You add X to one side, H to the other. X can be chlorine, bromine, or iodide. Like 95% of the time, it's just chlorine or bromine. Right. So we've gone over the mechanism, and we're going to go over it again to talk about some more stuff. The first step is an electrophilic addition, right? I'm adding my double bond to an electrophile. So I take I'm going to start it on the next page. So I have this, you remember, take HX. Hydrogen is slightly positive. Halogen is slightly negative. So my pi bond electrons attack the hydrogen. Hydrogen gives its electrons to the halide. I make a carbon hydrogen bond. Plus I make Br minus, and then my Br minus adds to my carbocation, which I just said a word there that I need to teach you. Why did I make it a bromine? I don't know. Why did it stay an X? Established. Bad at my job. There you go. Haha. So, during this reaction, we make something called a carbocation. Right? So, a carbocation, carbo for carbon, cation for positive charge. You generate a carbon that has a positive charge. So we're going to talk about the structure and stability of carbocations because that's important for predicting what products we're going to make, right? So for carbocations, so they're bonded to 3 other groups and they have an empty p orbital. So you've got your carbon, and your carbocation looks like this. So the methyl, the ethyl, and the hydrogen are all on the same plane. So I'll hold this up for zoom as well. So your carbon looks like this, right? It's just this, and then that p orbital is sticking right through the middle of it, straight up and down. So I'm drawing it with the wedges and the dashes because right, the ethyl group is forward, the hydrogen's back, and then the methyl group is in plane, like it's in the plane of the page. So it's you kind of got this flat, almost like a triangle within the p orbital sticking straight up and down through the carbon. So a positive charge on an orbital means that orbital is empty. It has no electron. So this is our empty p orbital. Okay. Now you might remember I put the positive charge on the top lobe of the p orbital, but that whole orbital, both sides are empty, right? That's just one orbital, right? So carbocations are flat, and this is important for determining stereochemistry of the reactions. So right, so again, I'm going to redraw that. Right, so what this means is when I go to add my halide, I have an equal chance to add the halide from the top to the top lobe or to add it from the bottom. So what this means is half the time, this is H here, sorry, half the time I add my halide from the top, and the other half the time I add my halide from the bottom, right? So I get a 1-to-1 mixture of these enantiomers, right? So I don't make one chiral center because I have a 50% chance of making the R and a 50% chance of making the S. So you always are going to make a racemic mixture. Right? Half the time you add from the top, half the time you add from the bottom. So we can never just make R or make S when we have a carbocation. We always make a mixture. Make sense? Right? Since it's flat, there's nothing to bias which side the nucleophile comes from. It just comes from whichever side it happens to be on at that time. Okay, so carbocations come in 4 flavors. I assume they're all like the nasty like jelly beans from Harry Potter. They're like bogey and earwax. I assume they're all bad, but there are 4 flavors. Right. So the first type are tertiary. Right. Your positive. Oops. Your positive carbon is bonded to 3 other carbons. So something like that, tertiary carbon, or tertiary carbocation. Then we have secondary carbocations. So we've replaced one of the carbons from the tertiary carbocation with a hydrogen. Then we have primary. Your positive carbon. Is bonded to 1 other carbon. So something like this, where now I've got 2 hydrogens on that carbon. And then you have methyl carbocations. So this is just a methyl group, CH3, and that carbon has a positive charge. So we have stability for all of these, right? And knowing this trend of stability is super duper important, right? So the most stable is going to be tertiary. Then you're going to have secondary. Then you're going to have primary. Then you have a really big gap, and you have methyl, or I guess just like, and this is our least stable down here. As a general rule, you are allowed to make tertiary and secondary carbocations. You can make these. Primary and methyl? No, we don't make those. They are so unstable that under normal reaction conditions, the molecules will just choose not to make a primary or a methyl carbocation. So almost every reaction, I think every reaction that we do, is going to either be a primary or a tertiary or a secondary carbocation. You're never going to have primary or methyl carbocations, right? So the question then becomes, why are tertiary carbocations more stable than secondary, which are more stable than primary, more stable than methyls? And it comes down to the number of carbons bonded to the positive carbon. So carbon is an electron donating group. It will share its electrons with other carbons to help ease the burden of having that positive charge. So if you have 3 carbons around the positively charged carbon, they will all donate a little bit of their electron density to the carbocation to make that carbon slightly less positive. As you put hydrogens in place of the carbons, hydrogen doesn't donate electrons, right? So each carbon you replace with a hydrogen makes the carbon with the carbocation more positive, right? Because it has less help carrying the burden of having that positive charge. So let us think of a carbocation as a couch. Your stoner friend's not on the couch right now, but it's a couch. And you've got to move this couch to a 3rd-story apartment, right? Carbon is your cool friend that comes over and helps you move it. When you're a tertiary carbon, you have 4 friends. Each person grabs a corner on the couch and helps carry it up the stairs. It's not too hard, right? All the friends pitch in, help carry the burden. Hydrogen's your friend that comes over, drinks your beer, and goes, whew, that couch looks heavy, but doesn't help, right? So now, if you have one friend who just drinks your beer and doesn't help and supervises, right? Now there's 3 of you trying to carry this couch up the stairs instead of 4. So it's a little bit heavier, right? You have to do a little bit more work. If you have 2 friends that aren't helping, there's one person on the front of the couch, one person at the other end, and it's a lot heavier. It's a lot harder, right? And if all your friends suck, you've got to put that couch on your back like you're carrying a backpack like Dora the Explorer and get it up the stairs yourself. And eventually you're just going to like collapse and like slide down the stairs. It's going to be awful, right? That's hydrogen. Hydrogen just doesn't help. So the more hydrogens that are around that carbon, the heavier the burden of that carbocation is. The harder it is for that carbon to carry that positive charge. Right? So why does carbocation stability matter? Why do we care about carbocation stability? Because what happens when we have a double bond that isn't symmetrical? Right? So our first example, right, was this, and let's add HCl to it. And it doesn't matter which side gets the hydrogen and which side gets the chlorine, because they end up being the exact same thing, right? You make this or this. If you name these, they have the exact same name, right? They're both 2-chlorobutane. So it doesn't matter which side gets the hydrogen and which side gets the chlorine, because you make the exact same product. Now, what happens if you have this? You can make 2 different products, right? You can make, we'll color code them. You can make this where you add the bromine to the carbon on the end, or you can make it where you add the bromine to the carbon inside of the double bond. I get 2 different products. How do you know which product is the product that you're supposed to make, that you're supposed to expect from the reaction? Well, you can think about what carbocation gets made in the mechanism, right? So if you remember, wherever your halogen ends up in your product, there was a carbocation there before, right? So if we just go back a step, what kind of carbocation is the red one? It is primary. What kind of carbocation is the green one? It's bonded to two carbons. Secondary. It's directly bonded to two carbons, so it's secondary. What's more stable, primary carbocation or secondary carbocation? Secondary. So if given a choice, the molecule is always going to make the more stable carbocation. Molecules in reactions take the path of least resistance, right? So if given the choice between making a primary carbocation and a secondary, the molecule is going to make the secondary carbocation, and we're going to get this as our product, right? Because this is more stable. So we're going to make more of this carbocation, which means we're going to make more of the product that we get from that carbocation. So you can just predict based on carbocation stability which of the two products you're going to make. More stable carbocation equals more stable, equals more of that product. So, of course, there's a rule for this that like even kind of strips out the even to thinking about the carbocations. That rule is, I have to make sure I don't misspell this guy's name. The mark part is easy, but then it gets all Russian on me. So there's Markovnikov's rule. And Markovnikov's rule says when adding HX to a double bond, the H is added to the least substituted carbon of the double bond. So Markovnikov's rule says adding HX to a double bond, H is added to the least substituted carbon, so the carbon that has the least non-hydrogen things on it of the double bond. Another way to think of this is you look at your double bond and you say which carbon has the most hydrogens. That's the carbon that gets the hydrogen from the HX. So this meme has come and gone. Hydrogen wants to crack open a cold one and hang with his boys. So the hydrogen wants to go hang out with other hydrogens. So my early class was like, so he's a frat boy? I'm like, sure. Their frat is HHH. There we go. So you can just look at a double bond and say, okay, we'll say HCl. HCl. And you can say, okay, how many hydrogens are on the red carbon? None. How many hydrogens are on the orange carbon? 2. 2 is more than 0. So we're going to put the hydrogen from the HCl on the orange carbon. and the chlorine goes on the other carbon. Right? This works out, right? Markovnikov's rule was kind of developed before we had an understanding of carbocations, but it works out that it makes it so you follow that you make the most stable carbocation. Because when I put the hydrogen on the end, right, I make a tertiary carbocation. When I put the hydrogen inside, I make a primary carbocation. So I don't want to make this because it's less stable. So I make the tertiary carbocation, and then my chloride adds to that. This is the point where I often bring up that, like, I apologize if you're colorblind, since I just color code everything. If they're all just gray dots to you, I'm sorry. All right, so am I going to put the bromine on the red carbon or the orange carbon? The bromine goes to the orange carbon because the hydrogen goes to the red carbon. So we're going to end up making that. Change up my colors for some reason. Got blue dots and red dots now. Where's my chlorine go? I'm hourly, it's fine. Where do I put the chlorine? Does the chlorine end up on the red dot or the blue dot? Red dot.
I was asked what you were supposed to get out of this or what you should be trying to look for when you're doing these examples.
So what we're looking for is, so Markovnikov's rule says, look at your carbons and say, okay, the red carbon has no hydrogens on it. The blue carbon has two. So Markovnikov's rule says, put your hydrogen on the carbon that has the most hydrogens. So in this case, the blue carbon, which would be here. And then that means the halogen goes on the other carbon, right? So you can kind of shorthand that and just be like, okay, which carbon does my halogen go to? So what you can think about is if your hydrogen goes to your least substituted carbon, the halogen goes to the most substituted carbon. Right? Because since we're drawing skeletal structures and the hydrogen's understood, we don't have to always draw that hydrogen in. So we don't have to like draw that the hydrogen's there. If you did this, right, you would know there was 3 hydrogens on the blue dot carbon, right? I don't have to show you that hydrogen. So it really boils down to where are you putting the chlorine? That's the thing that you have to show after the reaction's done. So it's your hydrogen goes on the least substituted carbon, which is the carbon that has the most hydrogens, and your halogen goes on the most substituted carbon, which is the carbon that has the least number of hydrogens on it. So that's what you're looking for. Markovnikov's rule says look for the carbon with the most hydrogens. Put the hydrogen there. But you can turn that around and say look for the most substituted carbon, put your halogen there. And it just works out that by putting your halogen on the most substituted carbon, you're also making the most substituted and as a result most stable carbocation. So this is, even though these examples are relatively simple, this is what I meant when I said in last class that it's not a point of you like memorizing all the examples I've done in class. It is like being able to look at a molecule you've not seen before and, predict, I've not seen this molecule before, right? And maybe I've seen something similar, but I've not seen this. How is this reaction going to work? Well, I know Markovnikov's rule. I know that when I add HCl to a double bond, I add a hydrogen to one side, chlorine to the other. Markovnikov's rule tells me which side the hydrogen and chlorine go on. I can know what this product is, even though I've never seen this exact reaction before, right? So the point is being able to take the rules that I give you and apply them to any structure that I give you and be like, oh, okay, I know that double bonds react with this to make these kind of products. I know how to predict what these, it's called regiochemistry, which side gets which group, and so I know what the product's going to be. So I should be able to give you anything like on an exam, and you should be able to go like, oh, I know that I end up with that as my product, even though I've never seen this particular reaction before. So it's being able to apply those rules as opposed to like just knowing like, oh, A plus B is C, right? Because I've seen it before. I've never seen A before. I've seen this agent. I've seen B. I know how they should react. I can predict the product. So don't get hung up on like, oh, he gave us 20 examples. I need to do all 20. It's like the examples illustrate the rules so that you can apply the rules to anything that you see. So that is that little spiel. And if no one has any questions or anything, I think we're good.